Hey everyone, Mr. Cummings here, and welcome to this video on representing motion with position and time. So we have four main ways of representing position and time, and that is with the motion diagram, motion equations, position time graphs, as well as written and descriptive. We'll start by taking a look at the motion diagram, which essentially just shows where an object is located at evenly spaced time intervals. So we're going to look at constant motion, accelerated motion speeding up, and then accelerated motion slowing down. So if something's moving at a constant rate, what we're going to see is every single dot that we see is indicating where the object is located at an evenly spaced time interval. So each one of these dots is 2 units apart, and each dot is indicating maybe a second in time. If we take a look at accelerated motion speeding up, what we should see is the first few dots are pretty close together, but they gradually get more and more spaced out, indicating each subsequent second the object is moving a further and further distance than the second before it. If we take a look at accelerated motion slowing down, what we're going to see is the reverse of the speeding up, where we're actually traveling quite a far distance in the first few seconds, and then that distance is getting shorter and shorter as the time progresses. So we can take a look at 2 real-life examples of this. The first will be a runner accelerating from rest down a track, the second being an apple free falling from a tree, one being horizontal motion, the other being vertical. So if a runner is starting on a start line, what we're going to see is they're going to start off with a pretty low velocity, or velocity close to 0, as they gradually get faster and faster as they run down the track. So we should see the dots getting further and further apart as time progresses. So we can make motion diagrams for vertical motion as well. So for this apple falling from a tree, it's going to start with some initial velocity of 0 and then gradually get faster, meaning it doesn't cover very much distance in the first time interval in which it falls, but that distance gets bigger and bigger as the apple gets closer to the ground. It's picking up speed. So when looking at a function that tells us where an object is going to be located in time, we get a position function that depends on the time squared, and that's because as the time progresses, we're covering more and more distance every single second. So we have a quadratic relationship with time. Now in this equation, the x variable is going to indicate the position of where the object is located at some moment in time, at some value of t. The x with a subscript 0, we call x naught, or initial position, is telling us where the object is starting. So at time 0, what is the object's position? Now the next term in this equation is vx naught times t, or the initial velocity multiplied by the time. And what this term is telling us is how far is the object traveling due to it having some initial velocity multiplied by the time that it travels. The final term, the 1/2 ax t squared, is telling us the displacement of the object due to the object's acceleration multiplied by the time squared. So now we'll take a look at using this equation for a couple different special cases, the first of which being when we have 0 acceleration. So when an object has 0 acceleration, it's said to be moving at what we call a constant velocity. So originally the equation had this added term, this plus 1/2 ax t squared, but when our acceleration is 0, we plug in 0 for ax and it gets rid of that entire term. So what we'll do is we'll take a look at the example to the right where we have a battery-powered car. It's initially at some position -4 on a track, and at time t equals 0, the car is turned on and it begins moving with some constant velocity, +2 meters per second. We want to make a table of the car's position for time 0 seconds, 1 second, 2, 3, and 4. Now that we have our table set up, we're going to go ahead and just run through some calculations. So we know the initial position is starting at -4 meters, so we don't really need to do any computation there. Now for all of the other positions, all we really need to do is plug in the different times into the equation. So for 1, we'll plug in -4 plus a velocity of +2 times 1 second, and we'll just compute that arithmetic, and we will figure out where that object is located at time t equals 1 second. We'll do the same thing for x subscript 2, 3, and 4. Now we'll take a look at another special case where the object is accelerating starting from rest, meaning there is no initial velocity. Remember, this equation now is modified. There used to be a v initial x times t, but when v initial x is 0, this entire term goes away. So what we'll do is we will do the exact same thing. We will make a data table, and we'll compute the values for x at times t equals 0, 1, 2, 3, and 4, and see how this object moves at those different times, and where the object is located at those different times. So once again, at time t equals 0, we know the initial position already. It's going to be located at x equals -4. I didn't need to do this computation, but you can see how we're going to plug the numbers in this example equation here. And so now we'll run through the calculations for the position at time 1, indicated by x subscript 1, position at time 2, 3, and 4, and we'll populate our data table. So we've copied and pasted both data tables so that we can compare their displacements over time. What we're going to do now is we're going to make another column here that's going to represent the displacement of the object in between two time stamps. So we'll take a look at the displacement between time t equals 0 and t equals 1, between 1 and 2, 2 and 3, and then 3 and 4. And we'll compare the displacement between the object that's moving with a constant velocity and an object moving with constant acceleration. So when we take a look at these new calculations, what we see here is in the constant acceleration, we start off not moving very far, 0.25, 0.75, so on and so forth, but over time, that displacement is increasing. Whereas if you take a look at the constant velocity, we're moving more, we're moving 2 units in the positive direction, so we're moving more than the constant acceleration to start, but we can see over time, the constant acceleration is going to end up moving more displacement than the constant velocity and eventually overtaking and actually catching up and passing it. So we're going to end this video by doing a quick modification to the equation that we were using before. So I prefer to use this modified version where we're actually not solving for the position as a function of time, and instead we're solving for the displacement as a function of time. Now, we're going to do a quick derivation over to the right. If we remember, displacement is simply the final position, or some position at time, some time, minus the initial position. So if we use that substitution, and then we just move the initial position over to the left-hand side, we can see that this equation has displacement in it. We just need to group the two position terms on the same side of the equation. Doing so allows us to then substitute the delta x in for x minus x naught, which gives us that slightly modified equation. And that's going to be it on this video on representing motion with position and time. Thanks for tuning in, and I look forward to seeing you next time.